Welcome to our last lesson on trig. In this lesson, there's actually only one word that will be new to you. Everything else will involve strategies that you already know, and you just kind of have to put together into solving new kinds of problems. So the only word that is kind of new to this lesson, the only thing that really is kind of new learning for you, is the word solve. Okay? We know this word, it's up on the wall in the classroom, and usually solve means that we are going to look for the solution to or the value of a variable. When we solve an equation, we're usually looking for the value of x or y or perhaps even theta. Okay? When we say solve a triangle or solve this triangle, we're looking for something very specific. What we're looking for here is the measures of all the sides and all of the angles of our triangle. So when we solve a triangle, when we're doing that, we're finding every piece of information, right? We have to fill in every unknown piece of information. So you're always going to get two pieces of information in a right angle triangle to start off with. And whatever pieces of information you get is going to help kind of determine what your starting point is going to be. So in this particular triangle, we're given two side lengths of a right angle triangle. So if we think about all of the strategies that we have and all of the tools that we have in our toolbox, we actually have a couple of starting points for this particular triangle. We could actually find the length of xz or little y, right? We could actually find the length of that by using a squared plus b squared equals c squared, right? We can use Pythagoras and go all the way back to solving that part of it in grade 8. If we were given one of the angles here, we could simply subtract 90 degrees and the size of that angle to find the third angle using our 180 rule, right? The rule that says that all the angles or the sum of the angles in a triangle is 180 degrees. And that doesn't just apply to right angle triangles, that's all triangles. But we only need one other triangle here because we're given this right angle here. Okay, so we've got kind of these two older kind of standby strategies that we can always use. But I'm going to use as much trig as possible here just to show you, just kind of keep practicing these new grade 10 skills. And my very strong recommendation is to always use the given information as much as possible. And what I mean by that is if I were to use Pythagoras to solve for little y, right, I would have 10 squared plus 6 squared equals 136, which isn't a perfect square. So when I square root that, I get little y equals 11.66190379. This is an irrational number. So if I round it too soon, then I'm not going to get as accurate results for my angle sizes if I use this, right? I want to use exact values as much as I possibly can, especially if your plan is to go into pre-cal. Okay, we need to keep exact values as much as possible. Okay, so we kind of know already that y is 11.66. Here, let's write that in. But we got to show our work. So let's say we know that this is little z, and we know that this is little x. So we're going to say x squared plus y squared equals z squared. And we did 10 squared plus 6 squared equals z squared. Z squared equals 136. So z equals the square root of 136, which is 11.66. Now that's only an approximate value. So we're going to try to avoid using this side length when it comes to these other two, to find these two angles here. We're going to use our given information as much as we possibly can so we get nice exact answers. Okay, if that doesn't make sense, send me a message and we'll kind of talk about that a little bit further. All right, so let's find angle X here. Okay, because we have the side lengths, we still need the angle measures. Side or angle X, the given information we have relative to angle X is this opposite, which is 10, and this adjacent, which is 6. So it sounds like we need to use some tan. So tan X equals opposite over our adjacent. And in this case, we have two thetas, or we have two unknown angles. So if we use theta here, it might be confusing because we won't know exactly what angle we're working with. Right, so we're gonna be really specific here. So we're gonna use big X to represent this particular angle. Okay, so let's fill in tan X equals, our opposite is 10 over 6. So X equals the inverse tan of 10 over 6. And again, we want to check to make sure in our calculator we're in degree mode, or we're gonna get this completely wrong. And we get X equals 59.036. So let's round that to 4 degrees. Okay, so we have angle X is 59.04 degrees. Now, it's not exactly 59.04, right? It's this number here, this irrational, well, this very long, yeah, very, very big angle size. So if I can actually now just use my 180 rule. I could use a tan ratio again to find angle Z, but I can also just use my 180 rule to find the size of angle Z. And that's a really tempting thing to just write down, but we always show where all of our information comes from. Okay, so if I'm just going to do a quick subtraction to figure out how big angle Z is, then I'm just going to write that down. Okay, and what I'm going to do in my calculator is, I already know 180 minus 90 is 90, so I'm just going to go 90, subtract this answer that I have. Okay, so I get, whoops, 30.96 degrees. Okay, so that's how big angle Z is. Now, again, I could have used a trig function. I could have kept all my decimal places here for Z and used different trig functions, right? I could use sine or cos because I've got the hypotenuse now. But I just, choose the kind of most simple, most straightforward way to get there. And again, show all of your work, especially just this tiny little step here. Lots of students forget that, and then they lose a mark because they didn't show where that angle came from. You can't make any assumptions that I know exactly what work you're doing. Okay, it's not about the answer, guys. It's really about the thinking behind it, and we want to show that any strategy that we're using. If you want to just say 90 subtract 59.04, I got that, that's fine, okay? But we do have to actually show how we determined the value of each angle size and each side length. Okay, so again, nothing new here. You know about Pythagoras, you know about the 180 rule, you know about using tan ratios and sine ratios and cosine ratios. So the only thing that's new is this word solve. Pretty easy. Solving a triangle means filling in all the side lengths. And anything that we give you to solve in grade 10 is going to require you to use a trig function at least once. Okay? And then you're free to use, make it as complicated or as simple as you like to find the remaining pieces. All right, if we take a look at the second problem on this sheet, we get a problem that has more than one angle in it, or sorry, more than one triangle in it, and we need to solve a side length. And what's really important to notice is that both of these triangles involve right angles. So we can use SOHCAHTOA for both of these. And there's a couple of problems in your independent practice where you don't have right angle triangles. And so I mean, you do for part of it, but not for the whole thing. So any triangle that you're going to use SOHCAHTOA for must have a right angle in it, okay? So watch for that in your independent practice. Okay, so let's take a look at this problem. We need to find the length of CD. So that's this guy right here, right? So it's part of a right angle triangle, right? This BCD triangle here. And we've got an angle size of 26, right? And so relative to that 26 degrees, we have an adjacent side. So it's looking like we'll be able to use tan or cos here, but we need another piece of information. Right? We only have one piece of information here, and we always need two pieces of information to solve anything. So where are we going to get that second piece of information from? Well, if we look at triangle ABD, we've got two pieces of information in that triangle, right? We've got this angle here, we've got this side length here, and we can use that to find the length of BD. And since BD is the same in triangle ABD as in triangle BCD, right? This length is going to be the same in both the triangles. So that'll give us that second piece of information we need to find that guy right there. Okay, so what we need is the hypotenuse of triangle ABD. Given angle 47 degrees here, and I don't want to call it angle B because angle B is really big, right? It's this big angle here, so I want to be really careful. This is triangle this is angle ABD. All right, so that can be a little bit tricky. So if we look, we have the opposite, and we're looking for the hypotenuse here. So we're going to use sine. I'm just going to put sine of 47 degrees equals the opposite over the hypotenuse. It's not really angle B, because angle B is this big one, or is it this part, or is it this part, right? It's kind of hard to tell. So I'm just going to be really clear here and calling it just the angle that is 47 degrees. Okay, so let's fill it in. Sine 47 equals, my opposite is 4.2. My hypotenuse is what I don't know. That's BD. So remember, we can just kind of switch these guys around because these are both factors of 4.2. So BD equals 4.2 over sine 47 degrees. So we'll put that in our calculator. 4.2 divided by sine 47 equals BD equals 5.742775337. Okay, and I know that's a very long number, but remember we'll write this down in our notes, it's really important. Don't round until the end. Okay, otherwise you'll get a rounding error, or you have a very strong possibility of getting a rounding error. Okay, so because it's a big long number, I'm just going to keep it in my calculator. Okay, and then we'll see how we're going to use this number here in our second calculation. So in this triangle, this BCD triangle here, again, we're looking for the adjacent, and now we have the hypotenuse, right? That's the hypotenuse. BD is the hypotenuse of this triangle as well. That's not always the case, but in this particular example, that's the way it works out. So we're going to use cosine. So we're going to use cos of our 26 degrees is equal to our adjacent over our hypotenuse, and cos of 26 equals, we're looking for the adjacent, so we're just going to call that x right now. I labeled it on my triangle, so it's not bad. I didn't introduce a new variable. I'm just going to call that x. I can call it CD though. Okay, and then my hypotenuse is this 5.742775337. Okay, and when I multiply these guys together, I already have this big long 5.74 blah 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 in my calculator. I'm just going to times that now, right? It turns into my answer, times cos of 26. So I get x equals 5.1 0.16, and we're measuring in centimeters. Okay, you can put all of the decimal places in your final answer, but you want to have at least 2. Okay, we want to be really careful because if we didn't have this big long number here, when we multiply it by cos 26, we might get something, well, we would get something different here, and it might round differently. So you would get a rounding error if you had anything other than 5.16. Okay, so just be careful of that. All right, and that's how we can use a trig ratio more than once in a problem. And you have a variety of problems in your independent practice to try out. Any questions that you need to kind of help you through them. They're kind of fun little puzzles to figure out sometimes too. Okay, good luck, guys.